Should be good. I can see myself, and it seems fine. Okay. All right. Sorry. Yeah, the internet just like freaked out for a second, and OBS disconnected. Okay. So, okay, you can at least see the things. Go away. Okay. Right. So you see that closed sets are in A are just intersections of closed sets in X with A. So then the question is the closure of Y in A just the closure in X intersect A? Right? Seems like a reasonable question. Can we just intersect the closure with A and still get the closure? So this is where I think it can be useful to think of maybe an example, right? If you're trying to determine like, is this true? So let's look at an example like, let's see, what's the one I'm going to use here in a second? Why am I writing C? Why? So let's check this out and then just have X be R, right? So in this case, we already know that Y is closed, right? And it's also closed in X. So in this case, like the closure of Y in X is Y. So it is 1/2 to 1. And obviously that is Y intersect A, or the closure intersect A. So this is equal to closure in A of Y. So here, like, yes, it's true. And you would find even if we took away an endpoint, that would work. But let's see if the same thing, so this is obviously not a proof. We'll prove this in a second. But I just want to analyze this example. What about interior? So is the interior of Y in A equal to the interior of Y in X intersect A? So using the same example, right, the interior in X of Y is 1/2 1, right? We just remove the endpoints. That's easy. We know how things are on the real line. What is the interior in A of Y? So this is stuff we did last time. So who can tell me what this is? Or type it, whatever works. But this is asking for Y inside A. You got to tell me what's happening with the endpoints. It's actually not the same thing. Well, I mean, it's 1/2 1. It's just one of these endpoints is actually included. They're not actually. Right. Remember, we have like 1/2 3/2 is open in X, and you just intersect that guy with A with standard topology. Right. This is the stuff we were doing last time where we can suddenly include endpoints because you've like restricted by intersecting with A. So yeah, you take some open set with X, and we can get 1/2, but include 1 suddenly. And so in this, yeah. which it is, right? Y includes 1. I'm confused. No, but that's not what I need, right? Like, I do intersect it with A, and so I get this guy, which lies in Y. This is what I'm claiming is the interior. Right. Yeah, so in this case, right, we see different results. So one has the point included, and so here we might guess that in general, maybe we have this inclusion, but not the other one, right? Would be a guess. So let's actually try to prove these things. Okay, so I mean, obviously that was one example, so it's not like the most illuminating thing in the world. Well, I guess it was more illuminating for the interior because we actually got a counterexample. But closure, I mean, hooray, it was true in one case. That tells us very little. So let's go ahead and actually prove it. So this is what, 150? Okay, so we've got y is contained in A is contained in X, and our goal is to show that the closure of y in A is the closure of y in X intersects A. Exactly, proof by example. Always works. All right, so you could go element by element. That's definitely like a reasonable thing to do. If you wanted to use like our theorem about like every open set would have to intersect whatever. But here I think it's actually more beneficial to just use the definition. Like, what are these things? Are the intersections of all closed sets containing. Okay, so let's go that route and just do a whole bunch of set equalities. So the closure of y in A is the intersection of closed sets containing y, but in A, right? So closed in A, containing y. Okay, well, by our theorem above, that was by 147, right? This is the intersection of C, or sorry, I guess I can rewrite C using that theorem as F intersect A, such that F is closed in X, and F intersect A contains Y, or, I mean, you could also say, I'll do that for now, and then if F intersect A contains Y, then F most definitely contains Y, right? And so that's kind of the real thing that I want, because I want closed sets in X containing Y to talk about the closure there. So this is F intersect A such that F is closed in X and F contains Y. All right, and then what do I need? I need to basically split off that intersect A, right? Because I just want to view the F containing Y by itself. But you can, right? The intersection is something that distributes. I have basically I'm looking at like, F1 intersect A, intersect F2 intersect A. The point is all of them are being intersected with A, so you might as well just do it one time on the outside, right? So this is equal to, that's kind of an aside, that has nothing to do with this. This is now A intersect, again, these closed sets, but now I've dropped the A there. Writing is hard. And that is exactly the closure in X. Right? So we get exactly what we wanted just by using the definition. Any questions on that one? No, we don't need to do like subset inclusion on each side. I mean, right, that would be more of an element specific approach. With this one, I'm just using the definition as this intersection of sets. And so here, all of these are equalities just by inspection, pretty much. They're just rewriting ways of saying the same thing. Okay. So, I mean, you could try to do the same thing for the union, right? And you would see at some point that it fails. Since we already saw the example, let's just try to prove the one way that is true, right? So, again, we saw with so for interior, we saw with our example here, that the interior of y in A contained, right, yeah. And so, right, like 151 basically says like explore the relationship between, right? This should feel somewhat like I forget exactly which question it is on your take home. I think it's the last one for the exam, right? It's more of like a figure out what happens, right? And so we found a counterexample, and so we know one of the ways does not include, and so we think that the interior of y in A seems to contain the interior of y and x intersect A. Which again, kind of makes sense because of what we do with endpoints. Right, there's no equality. Yeah. Right, because then it wouldn't hold in general if you found one place where it fails. So we know that the other one doesn't hold in general. It most definitely holds sometimes, but not in general. And again, the issue, right, is that open sets can include endpoints for like the realign and standard topology example if A itself includes those endpoints, because that intersection will suddenly include them. So that's basically the reason you can get extra stuff, because if you do the interior in X, you will never include those endpoints even when you intersect with A, right? Because you don't do it at like the top before you start intersecting. Okay, so in this case, right, I just want to show that this guy is included in that. So here, I think it maybe, I'm going to do an element approach. It's not too bad to do, and I don't think, I think we had like 78 and 79 were our big things on like the element specific ways to show something was in the interior closure. I think we've used the closure one so much more that it's nice to see the interior one used a little bit. So let X be in the interior of Y and X intersect A. Well, for sure, X is in A. And what does it mean to be in the interior? So this is the 78 statement, basically, right? That just means there's some open set, not all like with the closure, but just one open set at least that contains X and lies inside Y, right? So since X is in the interior of Y and X, there exists U open in X such that X is in U and that is contained in Y. So that's 78 for us. Okay? And if we have this open set, so what are we trying to show, right? We're trying to show that it's in the interior of Y in A. So we need an open set in A containing X that's also contained in Y. Well, what do you think we do? We just intersect this guy with A, right? We already have an open set. That's how we get open sets for A. And we're good, right? So X is in A, X is in U. So X is definitely in U intersect A. That's still contained in Y. And U intersect A is open in A. Thus, again by 78, X is in the interior of Y in A. Okay. All right. So this is the fun part. We're going to do some boundary stuff. All right. This will eventually, right, like boundary is going to be probably on the next problem set, which I've hinted at. I don't even think I've hinted at it. I've just kind of said that almost explicitly a few times. And so I just wanted to practice with it once. I figured we should do one together. So it's really not bad though, right? It's defined in terms of the closure and interior, and we already know what these things are. So I think we'll be fine. So let's just recall. Maybe I should not do the general one yet. So the boundary of yeah, sure. So let's just do the boundary of Y in X. So again, similarly, right, we have the boundary within certain sets. This guy would be the closure of Y in X, take away the interior. Okay, and then so similarly, boundary of Y in A is the closure minus the interior, but all inside A. And so our question again is kind of investigate. So is there some relation between these two guys? Do you guys have a guess as to what happens based on our previous analysis? So you are guessing, yeah, I think that's an excellent guess. You're guessing this. Right? The boundary is this. I mean, this is the definition. Yeah, in R2 or in R, it really is like the edge or like the visible boundary that you would call the boundary to a friend or an enemy. Just a human or a dog. I don't know. Whoever you talk to in your free time. But yeah, more generally, right? Like we talked about the example last time with the rationals, where like the closure is all of R, the interior is the empty set. And so the boundary of Q is all of R. And so that's just like super weird. But yeah, if you do it with like an interval or an open ball, yeah. Yeah, so that's the right intuition, right? So like this guy is potentially bigger. And if you are subtracting more, then you end up with less, right? So, okay. Let's first prove that the other way doesn't happen. So, is not true in general. Our first counterexample should still work, right? Because that's exactly an instance where the interiors are different. So we should be able to look at this guy exactly, yeah. Okay, and so what is the boundary of y in A? Well, the closure was y, right? And so it's this guy minus, and then the interior we included 1, so this was just the point 1/2, whereas the boundary of y and x intersect A is this was the same, the closures are the same, but then this guy did not have 1, and so we get 2 points instead of 1. So that would be a nice little example there. And so if we want to prove the other direction, then how can we do this? You can do it by like 78 and 79. For me, that seems harder. I think the other way would, again, be kind of using like these set things that are true, right? So doing this. So I think just like writing it out in terms of the definition of these sets, because we already have some relationship between these things, right? We already have some subset inclusions or equality in case of the closures. So we can use 150 and 150 or 150 and 151A basically to do this. So we have this, and then eventually we want to compare this with the boundary of boundary of y and x intersect A. So I'm basically going to translate these, right? So I'm going to first use by 150, right? This is the closure in x intersect A minus this interior. And then if I substitute in for this guy with the interior, right? That is where I suddenly do not have equality anymore. I get subset because this guy could be bigger, right? And so this becomes subset now, potentially. And I'll just put parentheses around this. So this is interior of y and x intersect A. And this is something I think we actually proved way back in chapter 0. But if you want to convince yourself, I mean, you can just do like De Morgan's laws over here. But basically, you can pull out the intersection with A, right? Because in both of these cases, you're saying it's in here and in A, but not in here, but it's still in A, right? And so the key is that this guy is equal to the closure minus the interior intersect A. Right, because the point is it's in this, it's not in this, which is this statement, and then it's still in A. So yeah, it's in A. So that's why these are the same. And this is exactly equal to what we want, right? So why did I write interior? Boundary, that's not the eraser. Boundary, intersect A. And so this subset here is what we need. How do we feel about that? Sure. Okay. Yeah. So what I'm doing here, right, is I'm just substituting one step at a time. So basically I'm looking at this closure and using 150, I just turn it into a statement about the closure in X. And then my next step is look at this part. And so here, right, I know that the interior of Y and A may contain, strictly or not, I guess, so contains at the very least, this guy. And so if I subtract it, I am subtracting at least as much. And so that's why this thing is now smaller or at most the same size as this guy when I replace the interior of y in A with the interior of y in X intersect A. And so then the last step here, right, because this one's just direct substitution. Oh, sorry, question? Right. And just when you're saying that, so you want to flip those, right? So it's the interior of y in A or the closure of y in X. The subscript is the thing you're in. Yeah, yeah. Okay. Right. Yep. Cool. All right. Nice. So that gives you a little practice with boundary. And again, really, it's just like all you did is add set minuses to things you've been dealing with a ton with the closures and interiors. That's why I skipped it, because you already have the skills to deal with that if you know the definition. Okay. So now we are ready for the product topology. And you can kind of see, like, we're moving quicker through topics now because we already have all our tools. Like, think about what new tools we've gained. Essentially none, right? We've just had definitions and we've applied things we've already had. So the product topology, now it's a little more complicated than the subspace topology, but let's just think kind of very basic. So let's think of like R2, right? This is a product, right? I mean, we can think of it as just, I've got my plane, but you can also think of the plane as line cross a line, right? And so what are our open sets over here? Well, if you have the open balls, it's not really clear how you're getting it from these. But if you view the open rectangle definition for the standard topology, right, like open rectangles are exactly things that look like this, right? These are open rectangles. Well, what are these guys individually, right? These are open in R. They're exactly the open intervals for our standard basis in R. And so this kind of leads to a definition for an open set inside a product. Okay, now the maybe surprising thing is that it doesn't tell us what every open set looks like, but rather gives us a basis. Okay, so here's our definition. I mean, if you're following along the text, you can read it, but if you're not, that's fine. So X, Y are topological spaces, so they have their own topologies. We can talk about open sets in them. And then an open set, or I guess a basis, right? So we'll just call it script B. We obviously have to prove this in a second, that this really is a basis for a topology on X cross Y. Is products of open sets in X and Y respectively. Okay, so I think there are a couple of things to sift through here. So like, why open sets and not basic open? Yeah, it is the Cartesian product, Devin. So we'll see an example here in R2 in a second. Basically, that this gives us a way. So let me kind of motivate this a little bit, at least for why this is a basis and not just all open sets. So think about like disjoint intervals, right? So let's just look on the real-line up here real fast. So if you saw open interval, like this is absolutely open, right? And likewise, if you look in R2, if you have, maybe I won't do that because it's not clear that I'm not including my endpoint. Why is that not erasing? There we go. Oh no. All right, we're good. I'm gonna go 1, 2, 3, 1, 2. Okay, so let's just say we have this open rectangle, and then I go down here and I have this open rectangle, right? Then in R2, using the standard basis, right, of open rectangles, this is definitely an open set, right? But this is not a product of open sets in R. Because if you do, like what is this? This is exactly 1, 2 cross 1, 2. And this guy is 2, 3 cross -1, -2. Jeez, -2, -1. We work left to right. Then if you take the union of these, or sorry, the products of the unions, right? Then like 1, 2 union 2, 3 cross -2, -1 union 1, 2 would give you extra stuff, right? So that would basically suddenly include this guy, and it would include this guy. But these aren't in there. So basically you would get like, you want 2 things instead of 4, but if you do the product, you're going to get 4. So this blue union red here is not a product of intervals. And so this would not be a product of basic open sets. However, it is the union of them, right? And so this is why this only gives us a basis and not the whole topology. So it's a little bit weirder than the subspace where we're just like intersects open with open. This one isn't just open is product of opens, that's a basis and you can get more stuff. This is an example of more stuff that you could get. Well, you can get more than rectangles from, right? Like you can get like, yeah, unions of rectangles is what you can get from this basis. So for instance, like this guy, right? Like these are two, this would be like a U and a V, right? These are still open sets in X and Y. And so that would give you like 4 rectangles and that would still be a basic open. But the point is you could never get the like 2 diagonal guys as a basic open in the product topology. Yes, yeah, exactly that. Exactly that. Okay. So, yeah, product topology is a little bit weirder, but not too bad. I mean, you get used to it pretty quickly. You just have to realize like, okay, it's a basis and then I can take unions from here, right? So, let's show that this genuinely is a basis, right? I made that claim. I should prove that claim. All right. So, this is 153. That B equal to the set of U cross V X, V open in Y is a basis for a topology on X cross Y. And the topology it's the basis for, right? The topology generated by it is called the product topology. All right. So What do I need to show? Well, no, you're trying to do a topology, right? We don't need to do quite that much. We just want a basis. I mean, you're right; those are open, but yeah. It's not that weird. So I want you to be careful there. So in this case, right, these are just open sets. These are not basic open sets. Yeah, they lie in there, but like we're not given a basis there. I don't think we need that. I mean, it turns out that it's true. So like 155 is actually that like you get a basis by taking U and V to be only basis elements. So it turns out that like that is all you need. But yeah, here that's not the claim, and then you'd have to deal with like unions of basics, and I just think that that's more work that needs to be done on this one. Yeah, so we just take a general thingamajigger here, right? We have our general little xy. We need to find what it's in. Well, wow, we already did it, right? Like x is open and y is open. So x cross y is already in script B. So we're good on that one. And then the next one would be that if it's in two of these basic open guys, then is there one contained inside, right? So let x, y. Yeah, yeah, yeah. You would just never write that, right? But yes. Right. Yeah, that's the only issue there, right? Is usually we know the context. I guess if you're dealing with both simultaneously, then you would use the one you've written on the left. Similar to when we had to deal with like the 1-2 cross in, right? And I called them like AI and BI so that you didn't have like an interval of intervals, which is like just weird, or an interval of ordered pairs. Sorry, that's just like, yeah, weird notation. And so yeah, this would be just kind of similar. But usually the context is clear. Okay, so right, it's in the intersection of two guys. So say this one is U1 cross V1, and it's also in U2 cross V2 cross. Well, we've actually proved a very long time ago. This is like theorem 13 or something. I don't know. It's way back. Again, this was back when we were doing the set theory. But this guy, and it's not hard to see this, right? Because like your x coordinate has to be simultaneously in U1 and U2, and your y coordinate must be in V1 and V2. And then it also turns out that like the converse is true. This is equal to U1 intersect U2 cross V1 intersect V2. Okay. And so this guy is open, right? It's the intersection of two open sets. So this is open in X. This is open in Y. And so this is, call this your B. But yeah, this is your basic open that's contained inside the other ones. So in this case, it's just the same. Right. Just that there is a basis element that contain. So for any element in your set, that there is some basis element containing it. Yeah. So here, it's just the whole thing is actually a basis element. So you're just good from the start. Yeah. Okay. So unions do not work the same way like this. You would not get equality here, right? We already saw that with the example up here, right? That like this union gives you the 4 rectangles, but if you have these separately, right, and then take the union of them, you would only get the 2 rectangles. So this is very much a product of, product is not intended to be used as like the math term product. It's a, shall we say, byproduct of intersections in general just kind of being nicer than unions in terms of preserving properties, right? That's something we've kind of seen as a theme throughout like abstract and vector spaces and stuff, right? Like unions, usually things screw up. The fact that U and V only need to be open sets and not basic open sets in 153. Yeah. But the proof is very similar. It's actually a little more work in 155, which isn't surprising because it's kind of the stronger statement. But yeah, we'll get there in a second. Actually, we're pretty much ready, right? So 154 was that example above, right? So, I mean, this is 154 right here. This is our example of not all open sets are of this form, U cross V. And your example would be the blue union the red. So blue union red is not U cross V. So we already have our example. And so 155, yeah, this is very similar. So here, right, we're given like C is a basis for X, and D is a basis for Y. And then the claim is we can actually do a bit better for our script B. We can actually do things that are C cross D, where C is a basis element in X and D is a basis element in Y. Okay, so again, I mean, you just have to do the basis stuff. It's just this one requires a little bit more just because we're talking about basis elements. So it's really the second part that's a bit harder. So if we just take a general point, right, in our Cartesian product, then we know individually, right, that there's some basis element of X containing little x, right? So there exists a C in C such that X is in C. There exists a D such that Y is in D. So XY is in C cross D. And C cross D is in B. Right, so it's just like a little more work, but follows almost immediately from the basis. And I think that's what Rippy was hinting at earlier, that like, yeah, you just take the ones individually. And then for the second part, right, so again, you start with something in the intersection of 2, right? So XY is in, say, C1 cross D1, intersect C2 cross D2. And then basically the point, right, is this is equal to C1 intersect C2 cross D1 intersect D2. And then each of these are bases. So what do we know with regards to these things? No? No? Right. Yep. Good. Yep. Cool. And then we're good, right? Okay. So the last little bit here is just kind of picture mode. All right. So want to draw some stuff, get an idea of like what are products, right? So like start thinking about like what are these spaces when we take Cartesian products. So a good one, right, is 156. This comes up a lot, and we actually talked about this, I think, a while ago in class, a little bit, not as formally, I suppose, right? So this, and give it like the standard subspace topology. I can. I mean, probably before, at least during lunch. This is my one day where I can't do my Thursday office hours from 11 because I have that oral exam makeup, or oral comp makeup. But I'll still be around after 2 today. But yeah, so if I don't get it done before my 11:10 Zoom meeting, then I'll do it during lunch. All right, so what is S1 cross I? So remember that S1 is the unit circle. Yeah, yeah, it's exactly a cylinder. Yeah, so like basically I just think of it like vertically because I like drawing my cylinders vertically. So you just have like a unit circle down here, and then you have the unit circle scanned all the way, right? You have like a circle for every point on the line segment from 0 to 1. So you're just like scanning it up. You have a line segment's worth of circles. And so you get this. And the key here, right, this is hollow. There's no interior because S1 has no interior, right? So this guy is hollow. It's just the border. So it's really like you folded up your paper, right, and just went boom. And there's nothing in between. Yeah. And then let's look at one more and talk very briefly about open sets because this has to do with what we closed with last time when we talked about the basic opens for the subspace topology on S1. So we did S1 cross I. What is S1 cross S1? Hollow ball. Yeah. So it's a sphere. Yeah. Right. So like you can start with your equator basically, and then just like you go all the way around, and I'm running out of flexibility there. The unit sphere. It is indeed the unit sphere. And since I can't draw like that, yeah, so it's the unit sphere. All right, I got him. Okay, so then the last part is to talk. Actually, yeah, no, we have like a minute I can use here. So remember last time we talked about the standard topology when we used it as for S1, right? The subspace topology there, given by the standard topology on R2. If you used open balls, then your opens, basic opens for S1 are arcs, right? And so if you wanted to look at S1 cross S1, the basic opens would be products of these, right? So you'd have like an arc cross an arc. What does this look like? Well, it's an arc's worth of arcs, right? So it's like you do this, and it's like the same on each side, right? So these little like patches on the sphere are your basic opens. And then, right, if you use the rectangles, we were able to get unions of arcs, right? You could get like this cross this or something, or you could do just like one, for instance. You like do a vertical rectangle that intersects twice, then maybe this guy intersects once. And so here it would be this union. And so you'd have like this guy, union, the patch where you're coming up from the bottom. So the upward facing guy. So you'd have like two patches together. And so these would be your basic opens. And then obviously like unions of those, and you can like patch up your entire ball. And again, it's hollow, right? Two arcs cross two arcs would just give you four rectangles. Right, it'd be the four possible combinations, basically. If that's hard to visualize, think about the four rectangle thing we had way up here. Right? So it's like 1, 2, union 2, 3. Anything in there, right? And so, I mean, it's maybe easier to see if they're actually like separate, not separated at 2, right? And do something like maybe distance 1 in between. But the point is, right, you could take anything in 1, 2 with anything in -2, -1, that gives you one rectangle. Anything in 1, 2 with anything in 1, 2 gives you another rectangle. Anything in 2, 3, anything in -2, 1, third rectangle, and then 2, 3, and 1, 2 gives you your fourth rectangle. Right, so that's kind of like what's going on there. And so with your arcs, right, it'd be the same basic idea. I mean, I can do another one, and yeah, so then you would just get this and this. Which kind of makes sense, right? I mean, this is, S1 is basically like R2, except for now you've got like this curvature, right? And so like the four rectangles becomes four of these like curved rectangular patches, right? But it's basically the same thing that's going on. All right, I'm gonna go ahead and in stream, and I can take like 2 or 3 minutes to talk.